This lesson is on intermolecular forces. These are often referred to as the van der Waals forces. These are the attractive forces between molecules, emphasizing the word between molecules. These are not intramolecular forces. Intermolecular forces are the forces that are within molecules, and actually, in other words, they actually form the molecules. And so here, if we have two molecules, each of these molecules is going to be formed by the intramolecular forces. They are the covalent bonding, if these are covalent molecules, and the intermolecular forces shown here in the red dashed line is what joins one molecule to another molecule, so they are between molecules. These are responsible for determining many physical properties of substances, such as their state, whether it's a solid, a liquid, or a gas. They determine things such as boiling point, freezing point, vapor pressure, solubility, responsible also for adhesion between different molecules, cohesion between like molecules. Many adhesives, such as tape, glue, depend on these intermolecular forces, or what are sometimes referred to as the van der Waals forces. The three primary van der Waals forces are the dispersion force, dipole interaction, and hydrogen bonding. This is in order of increasing strength in general. In general, meaning dispersion forces can get quite large if you have very large molecules, as will be seen later. The simplest van der Waals force to understand is the dipole interaction. A dipole is a molecule with a permanent and fixed polarity. In other words, it has a positive pole and a negative pole. So two poles, dipole. And the dipole interaction is simply the attraction of all the negative charges for the positive charges, making all of these molecules then bond together. To understand bond polarity, we need to look at the electronegativity of the elements involved. So here we have an electronegativity table and some bonds between elements. If we look at the oxygen-fluorine bond, we find the electronegativity of oxygen to be 3.5, fluorine to be 4.0. And so the electronegativity difference is 0.5. And then by referring to this lower table here, 0.5 is going to make that a covalent, moderately polar bond. In other words, the electrons are shifted towards the more electronegative fluorine. In the oxygen-oxygen bond, here the values are 3.5 for each atom, making the electronegativity difference 0. And so that is going to be a covalent nonpolar bond. And that's going to be true for any diatomic molecules such as H2, N2, F2, Cl2, any atom or molecule made up of the same two atoms. Looking at the hydrogen chloride bond, hydrogen is 2.1, chlorine is 3.0 from the electronegativity table, making the electronegativity difference 0.9. That turns out to also be a covalent, moderately polar bond, and we can show that polarity of the bond like we did above with an arrow and a positive sign indicating the shift of electrons. We can also use a sigma positive to indicate this end of the bond is positive and the other end sigma negative, indicating that end of the bond is negative. If we look at potassium and fluorine, potassium is 0.8, fluorine is 4.0. That makes the electronegativity difference 3.2. That means this bond is actually an ionic bond and not a covalent bond. And so we need to get rid of this line. It indicates a shared pair of electrons and indicate that this is a positive ion, this is a negative ion. Here the electronegativity is so different that there's actually a transfer of the electron from the potassium to the fluorine. So now we have a positive ion, negative ion, and the bond is formed by the electrostatic attraction of opposite charges. In other words, it is an ionic bond and not a covalent bond. Again, for dipole interaction, you must have a polar molecule, which is going to involve a polar bond someplace, but do not confuse polar bonds with polar molecules. Polar molecules have to be asymmetrical in terms of shape and electronegativity. All symmetrical molecules in terms of shape and electronegativity are non-polar. If we look at two linear triatomic molecules, we can see they can be either polar or non-polar. If the two atoms on either end are the same, again, that's going to make an electronegativity difference of 0. It's going to be non-polar. If they are significantly different, then they are going to be polar. The electron is going to shift from the less polar or less electronegative hydrogen to the more electronegative chloride ion or chlorine atom, making that a polar bond. Same thing in the linear triatomic. If the peripheral atoms are both oxygen and the central atom is carbon, here the electronegativities are equal and opposite, making the molecule symmetrical in terms of both shape and electronegativities. Overall effect being a non-polar molecule. So the non-polar molecule has a polar bond, but an equal and opposite polar bond, canceling the polarities out. So the molecule as an entirety is non-polar. If we have unequal polarities of the peripheral atoms, say we have a oxygen on this end, sulfur on this end, the oxygen being more electronegative than the sulfur, now we've got one end gaining more electrons because one end is more highly electronegative than the other end. That makes the overall molecule polar. It is not symmetrical in terms of both shape and electronegativity. Same for the trigonal planar. Here we have a molecule that is symmetrical in terms of both shape and electronegativity. All the peripheral atoms are oxygen. All have the same electronegativity, and the whole molecule then is going to be nonpolar. For the other molecule I have shown here, the oxygen is highly electronegative. That's going to make the electrons for the molecule shift towards that side, and that is going to be a polar molecule because it is asymmetrical in terms of electronegativity, even though it is symmetrical in terms of shape. Same thing for the tetrahedral. If all the peripheral atoms, in this case, in the carbon tetrachloride, all are chlorine, you have polar bonds in each of these bonds between the carbon and the chlorine, but because the overall shape is symmetrical, then they cancel out, making this a non-polar molecule, would not exhibit dipole interaction. But if we look at CH3Cl, this one is a dipole. It will exhibit dipole interaction because it is asymmetrical in terms of its electronegativities. The chlorine has a very high electronegativity, so electrons are going to shift towards it, making that end of the molecule negative, leaving this end of the molecule positive. For the last two, pyramidal and bent triatomic, these are both asymmetrical molecules, so they will always be polar regardless of the electronegativities of the elements involved. Second type of van der Waals force is the hydrogen bond. Again, this is still going to involve a positive and a negative attracting each other. Here is the hydrogen bond. Again, it's joining one water molecule to another water molecule. It is an intermolecular force. This hydrogen is positively charged because it's attached to a more electronegative element, the oxygen, so the electrons are shifting away. This positive hydrogen then will attract the unshared pairs of electrons on a different atom which have a negative charge, creating this hydrogen bond. What makes the hydrogen bond special is the hydrogen ion. It's not really an ion, but when the electrons shift away, it acts more like a positively charged ion. Think of the hydrogen atom. It consists of one proton and one electron. If we take away that electron, the only thing that's left is a proton, and then it becomes a hydrogen ion. If this element is a highly electronegative element, an oxygen, a nitrogen, or a fluorine, it will pull the electrons enough away to make this hydrogen atom act more like the ion, more like a proton, something that is very small without any electrons around it, which allows it to get very close to this unshared pair of electrons, making that a very strong type of dipole interaction, or what we call a hydrogen bond. And again, the hydrogen must be attached to a fluorine, an oxygen, a nitrogen, to have the electrons shift away enough to make that hydrogen positive enough to classify it as a hydrogen bond. So will all molecules with hydrogen bond? The answer is no. Again, it must be attached to either nitrogen, oxygen, or fluorine. So if we look at methane, methane has hydrogen in it, but it will not hydrogen bond because it's attached to a carbon, and the electronegativity difference is not great enough to make that hydrogen positive enough for it to hydrogen bond. So methane will not hydrogen bond. It's actually a non-polar molecule, so it would also not dipole interact. Same thing for hydrogen, H2. It is a non-polar molecule. The hydrogen is not positive in any way, shape, or form, so will not attract unshared pairs of electrons on other molecules. Ammonia, though, here we have the hydrogen bonded to a nitrogen, and the nitrogen is significantly more electronegative than each of these hydrogens, so the electrons shift towards that nitrogen, making it positive. And so this positive hydrogen here, or here, or here, will attract an unshared pair of electrons on a different atom, and that then creates a hydrogen bond between the two molecules. Same thing for ammonia and water. The nitrogen is more electronegative than the hydrogen, so electrons shift towards the nitrogen, or in the case of water, they shift towards the oxygen. But this is going to create positive hydrogens, which then can create a hydrogen bond either between the nitrogen and the hydrogen, or between the hydrogen of the ammonia and the oxygen of water. In both cases, these hydrogens are positive because they're attached to a more electronegative element, creating that hydrogen bond. Hydrogen fluoride will create hydrogen bonding. Again, the hydrogen is significantly less electronegative than the fluorine, and therefore the electrons shift towards the fluorine, making the hydrogen positive, and then it will bond to an unshared pair of electrons in a different atom, making that a hydrogen bond. Hydrogen chloride will not hydrogen bond. Chlorine's electronegativity is not high enough, and it's a large enough atom that just the physical properties of that size do not allow it to hydrogen bond. It's not strong enough, so this one does not. So again, it must be a nitrogen, oxygen, or fluorine attached to the hydrogen to make it positive enough to hydrogen bond. The dispersion force is the third van der Waals force. The main thing you need to understand about this is that this is involved in nonpolar molecules or noble gases, things that cannot hydrogen bond because they're nonpolar or lack hydrogen. They can't dipole interact, and so if they can't do either of those, then the only thing left is the dispersion force, and nonpolar molecules, noble gases, cannot do either of these, so the only thing left is the dispersion force. The other thing you need to understand is the dispersion force increases with increasing numbers of electrons. So if I asked you which of the noble gases exert the highest intermolecular attractions or the greatest dispersion force, the answer is going to be radon because it has the greatest number of electrons. And so nonpolar molecules and nonpolar noble gases such as neon can only exhibit the dispersion force, and it increases with increasing numbers of electrons. If we look at the halogens, which are diatomic, in other words, they are made up of two fluorines or two chlorines or two bromines or two iodines. Again, these things cannot hydrogen bond because they don't have hydrogen. They cannot dipole interact because they are nonpolar molecules, being diatomic. And the one that exhibits the highest intermolecular attraction, of course, is again going to be the one with the greatest number of electrons, which is iodine. Iodine turns out to be a solid under normal conditions because it has relatively strong molecular attractions. Bromine is a liquid, has weaker than iodine, but it is stronger than the chlorine or the fluorine, which are gases under normal conditions. Again, as you increase the number of electrons in the molecule, the dispersion force increases, making the freezing point go up, boiling point go up, making it more likely to be a solid or liquid under normal conditions. What causes the dispersion force? If you look at a single neon atom, it is going to be a non-polar atom. All the electrons are distributed evenly around the nucleus of the atom, but the electrons are in constant random motion. Not entirely random because they repel each other, they try to get apart from each other. But to visualize this, imagine a single neon atom which just by chance all the electrons happen to move towards one side, or just by chance they happen to be more on one side than the other side. That is going to give this a positive and a negative pole. We call that an instantaneous dipole, and it will induce a dipole in the next one. This negative pole is going to repel the electrons on this one, making the electrons move aside, giving this one a positive negative. And if you have billions and billions of neon atoms, this is constantly happening. They immediately revert back, but it's by the billions and billions of atoms all together, you have this collectively forming and unforming dipoles, induced dipoles, and that creates an overall weak but an attractive force between molecules. So which of these molecules would the dispersion force be the primary factor in determining the vapor pressure of it? Again, we're looking for things that are non-polar and or noble gases. So that would include chlorine, a non-polar molecule. Would not include hydrofluoric acid or hydrogen fluoride as a gas because this is going to hydrogen bond or dipole interact. It would include neon because it's a noble gas, a non-polar molecule, does not have a permanent dipole. Would not include potassium nitrate, that's going to be bonded ionically. It would include carbon tetrachloride, this would be a non-polar molecule, and it will also include butane because that is also a non-polar molecule. So again, dispersion forces are only in non-polar molecules and in the noble gases as the primary interparticle attractive force.